Good evening and welcome to MIT. It's great to see another large, exciting audience. I understand that most of you are here voluntarily. Ferdy, I think, did coerce all the students from Northeastern to come, but 95% of you, I think, are voluntarily. My name is Eric Adams, and I'd like to just say a couple words before we get on with the main program. There are 8 members of the Freeman Committee. I'm one of those members. And we are part of the Boston Society of Civil Engineers section of the American Society of Civil Engineering. And annually, the BSCE sponsors this event in honor of John Freeman. And Peter Richardson from BSCE will talk to us in just a little bit about a couple of the activities that BSCE does. As most of you know, John Freeman was a graduate of MIT's Department of Civil Engineering. We are celebrating our 150th anniversary this year. He was a member of the 15th class, so that takes us 90% of the way back to the place we started. After graduating from MIT, he became a world-renowned engineer. Locally, he's noted for having designed the Charles River Dam, the original one, where the Science Museum is. He also was instrumental in helping with the water supply system for a large number of communities, including San Francisco and New York City. Funds for this lecture come from a gift he endowed to the Society back in 1925, and its intent was to go for the education of young hydraulic and water resources engineers. And we hope that this lecture will convey some of the excitement on the water side of civil engineering, the civil engineering profession. In addition to putting on this lecture, the committee also gives out a few modest grants to students and young practicing professionals. A list of the past awards can be found on the website, which you can get to by simply Googling Freeman Fund. Also, you can download some of the more recent lectures if you like to catch one that you missed in the past couple years. If you are interested in applying for a grant, please let us know. And if you have an idea for a future Freeman lecture, also let us know. So with that, I'd like to turn it over to Peter Richardson, who will give you a few words about BSCE.
Thank you, Eric. I want to welcome everyone tonight to the 2011 John R. Freeman Lecture. I am a Senior Vice President with the Boston Society of Civil Engineers, and I want to thank the Department of Civil Environmental Engineering here at MIT for hosting this event, and also for the Freeman Fund Committee who puts this event together. I've been coming to these since the middle of the 90s, I believe, and every year they're a great lecture, and I think you'll enjoy it tonight. And the best part is they're free. So, the Boston Society of Civil Engineers is the oldest engineering society in the country. We were founded in 1848, and we are actually 4 years older than the American Society of Civil Engineers. We have 3,400 members, and we have 10 technical groups, and we run more than 50 events every year, including lectures like this, dinner meetings, and technical training courses. We have an active government affairs committee, an active outreach program, and also a very active younger members group. We publish an award-winning newsletter, which is put out 10 times a year, and then we also publish an engineering practice journal, which is put out twice a year. We work very closely with the ASCE student chapters. There are 9 in the state of Massachusetts, of which MIT is 1, and Northeastern as well, plus probably some other schools that are represented here. We are one of the largest and most active sections of the American Society of Civil Engineers. And this year, I just wanted to let you know about the 3 top priorities that are coming from ASCE. And they are competency, sustainability, and infrastructure, so CSI, if you to remember that. And for competency, the American Society of Civil Engineers is working to ensure that the next generation of engineers is competently trained to practice in this more complicated and changing world. And they've put together what's called the body of knowledge. And if you go and look at their vision for 2025, you can see what that is. It's basically a bachelor's plus 30 credits to sit for the PE exam. So this is something they're moving forward and think that's required for the minimum education. As far as sustainability goes, ASCE is teamed up with the American Council of Engineering Companies and also the American Public Works Association, and has developed a nonprofit institute, the Institute of Sustainable Infrastructure. And they are working on a certification program and then also a rating tool, which are going to be very similar to what LEED has been for buildings. Only this program is going to work to certify sustainable civil engineering projects and to make sure that engineers are trained in sustainable design. And the big issue there is the sustainability is the triple bottom line, so it's environmental, social, and economic, to make sure that we're looking at the full gamut of sustainability. For those of you that are not if you're students and you're not ASCE members, I would really like to encourage you to consider joining your ASCE chapter at your school. I think this is a great opportunity for you to grow in your career and start getting involved in your profession. You can get involved with concrete canoe competitions. You can get involved with Engineers Without Borders, or you can just come to our dinner meetings and the different activities at a very discounted rate. I can't encourage you enough to get involved at this point in your career. And then for those of you that are not students here, the engineers that are here, if you're not involved in BSCE, I would highly encourage you to get involved. The value of membership in an organization really comes down to how much you get active. And I can speak personally, being an active member of BSCE has helped my career tremendously. It's given me a lot of opportunities to grow in leadership, to be in charge of committees, to travel to Washington, to meet legislators, to write newsletter articles, to get my name out there, but most importantly, to give back to the noble profession of civil engineering. So with that, I would like to thank you and welcome you all to the lecture, and thanks for coming.
Thanks, Peter. And now I'd like to introduce Ferdy Hellweger, who's from Northeastern University, also a member of the committee, and he'll introduce the main speaker.
Thank you very much, Eric. I am honored to introduce this year's Freeman lecturer, my friend and colleague, Professor Vladimir Novotny. Dr. Novotny has had an outstanding career. He has received undergraduate and graduate degrees in sanitary and water resources engineering from the University of Brno in the Czech Republic. He also holds a PhD in environmental and water resources engineering from Vanderbilt University. He currently is on the faculty in the Civil and Environmental Engineering Department at Northeastern, where he has been since 2002. Before that, he was at Marquette University, where he served on the faculty for 20 years. He's also a partner at Aquanova consulting company. Vladimir has had a very productive career. He has published 14 books and over 160 articles. He has been active in the community, serving on various committees, including the National Research Council Committee to assess the scientific basis of TMDLs. And also he's the founder and served as the chair of the Diffuse Pollution Interest Group of the International Water Association. His service and accomplishments have been recognized with various numerous awards. Just as an example, he has been elected to the International Water Academy, and he has also been awarded the Sam Jenkins Medal, which is the highest award the International Water Association gives out. Now, rather than telling you about all of his accomplishments in detail, what I thought would be interesting if I tell you about Vladimir from my own personal perspective. So I first learned about Vladimir when I was an undergraduate student at Northeastern. And this was in the early 90s. And some of you who are familiar with the history of the field of environmental engineering will know that this was when the field was predominantly concerned with wastewater treatment. I took classes in wastewater 1, wastewater 2, advanced wastewater, biological processes in wastewater, physical processes, etc. You get the picture. But it was also the time where people just started to realize that point sources are no longer the big player, the big kids on the block, but it's the non-point sources that make up 70, 80% of the pollutant inputs to our water bodies. Now, when I was in my senior year, I started talking to some of my professors, and I sat down with a professor, and he asked me, what do you want to do in graduate school? And I said, well, I've been taking all these wastewater courses. I think I want to do wastewater treatment. And he said, don't do it. That's the past. And he told me the story about non-point source pollution, and he handed me a book, which was Vladimir's book that just came out in 1994 called Diffuse Pollution. And he handed it to me, and he said, take a look at this. Read it. This guy here, he's the leader of this movement. And I read it. I mean, it's a pretty big book. I skimmed over it. And it changed my career. And it changed the field of environmental engineering. Today, every civil and environmental engineering department, every consulting company, we all have people that look at non-point source pollution. And this was a revolution that was led by Professor Novotny in many ways. And, and today, Vladimir is not measuring concentrations in runoff like many other people are that are looking at non-point source pollution, but he's moved on. And he's asking different questions. And he's asking, how do cities function as systems? Let's look at the whole water system. Let's look at energy. Let's look at carbon. Let's look at the whole thing as a system. And he calls it cities of the future. And it's, the hottest new thing on the international global scale when it comes to water. It's cities of the future. And it's led by Vladimir Novotny. And so when I think about, who is this guy? What do I think about Vladimir? What do I say? I say, well, this is a person that leads large-scale revolutions and has led several large-scale revolutions that have changed the field of environmental engineering. And so I look forward to his talk tonight. He's going to be talking about his latest research project looking at cities and communities. And I have no doubt that, in 5 and 10 years, you will have one of those people studying this in every department and in every consulting company. And with that, I look forward to your presentation. Thank you very much.
Ferdi, who was that guy you were talking about? I would like to know him. Okay. It is indeed, maybe because there's so many young people here, and I really appreciate that you are here. Firstly, I have to say I'm immensely honored to be presenting the Freeman lecture, and I hope it will be a changing of changing something in your mind, the way you look at civil engineering, the way you look at now the integrated system. We are not just civil engineers anymore. We are now ecological engineers. We are now system engineers. We have to look and also at what's going to happen, what's happening on the global scale, and it is a fascinating new revolution. Ferdi actually put Professor Helberger, excuse me, he put actually very succinctly. This is again new revolution. We expect that we will be changing a paradigm of the civil engineering, a paradigm the way the cities are built, and I will be talking about it. So let's go to quickly through the slides. I have some outline. So I'm saying we will be changing the paradigm. It will be a new way we somehow build the cities, and I will also explain why it has to happen. It's not necessarily we will like to happen to be implemented. It has to happen because there is so many forces that are forcing us to do, forcing people to behave in a certain way. And this is a paradigm that we how we build a city. So the new fifth paradigm, there's a fifth, there were four paradigms before. So we will talk about the cities of the future. Cities of the future is a mainly acronym for this movement towards this new paradigm. And eco-cities are part of it. We will be talking that why we have to do it. It's urban metabolism. I will say I call it 4 R's, 3 S's, and 2 T's. Sustainability footprints. We go beyond this triangle of economics, ecology, and society. We're a little bit going beyond that. We have to go now, the triangle has to be also sustainable. This we will be talking about not the regional kind of regionalization. We will be talking about distributed systems and where you can implement this water and energy management together, and also ecology. We will be talking about eco-blocks, integrated resource recovery facility. We're changing a terminology, and it's not wastewater treatment anymore. It's an integrated resource recovery facility. So how we do that? Syngas, methane, hydrogen, towards electricity, nutrients, biomass, fuel, soil, solids, incorporating solar and wind power, sequestering GHGs. And there's already a lot of these things are happening, not in the United States, unfortunately, although there's some now promising developments. But mostly it's abroad, mostly it's in China, Singapore, Middle East, Europe, and so I will talk a little bit about this. I wrote an article in Czech language, by the way. After 40 years, I wrote an article in Czech language, and I call it, translated, Cities of the Future, Utopia or Unavoidable Reality. I obviously am for unavoidable reality, but again, some people may think it's an utopia. But there are some few quotations which may kind of help to start discussion. Urbanites now outnumber their rural cousins, and there's surprisingly good news. This is a surprisingly good food for environment, because the average person living in New York produces just 30% of the greenhouse emissions of the average US citizen, which is a surprising finding. And again, what's counteracting is that in the next 25, 30 years, there will, for example, China will have to build cities for 300 million people. They will have to build one New York City every year. So this is something which China is facing. And they're trying really very, very hard to face it in the right way, because they know if they don't, there might be a pretty bad catastrophe. I already introduced the cities of the future, and here is a picture of the Tianjin, which is now being built by as a consortium of China and Singapore, and near Beijing, about 150 kilometers southeast of Beijing. So I think they should be already. So we talk about this trinity of sustainability, society, economy, economics, environment, and things like that. The sustainability means that all these three are kind of in harmony. They have to. There is some kind of hydropolitical discourse in our area, but we are also saying that not only they're in harmony today, it has to be in harmony in the future. And now people are also saying, no, we cannot just make them equal. We have to see that environment is public health is a predominant issue in this sustainability discussion. So you know all of this. Sustainability is achieved when outcomes which are socially, economically, and environmentally sustainable are successfully contended in the intergenerational context. So originally was defined sustainable development as one that meets the needs of the present without compromising future generations. But again, we have these problems. The sustainability is compromised by this population increase. The largest increase will occur in urban areas, and not only that, in urban areas in developing countries. We have unbalanced hydrology. We have the hydrology is not functioning well. Because of the increased imperviousness, fast conveyance systems, mostly underground, so people don't see water on wastewater. They just see the impact on downstream. We have excessive use of water, and we have obviously high energy demand with excessive GHG, greenhouse gases emissions. So why fifth paradigm? Okay, so I put 4 pictures here for previous 4 paradigms. The first picture is from Athens, dates about 2,500 years ago. In 2,500 years ago, water was basically provided by springs and wells, and surface drainage was by gravity. And I was so excited when I saw this channel on this old marketplace on Athens, because it was 2,500 years. This is how they did it. This is not much different what you can see now in developing countries. The paradigm number 2 is long-distance water transport. Some of these aqueducts were, all Roman aqueducts, which are up to 50 kilometers. But if you go to Istanbul, which used to be a Constantinopolis, they had aqueducts coming from 400 kilometers. So they knew how to do that. They were distributing water by pipes, lead pipes and clay pipes. Sewers were invented, Cloaca Maxima in Rome, but there was again preceded by buildings on Crete and cities on Crete. Rainwater was harvested in Pompeii. They did it. They had rainwater harvesting. That's very common in Middle East and in Mediterranean. Some primitive treatment. So paradigm number 2. Then came industrial period. An industrial period that dramatically increased the pollution. Rivers caught on fire, as you saw the picture. It was the famous Cuyahoga River fire in Cleveland. Actually, there were several fires because of too much oil and too much junk coming into the river. So the people decided to cover the streams and put them underground, out of sight, no problem. This is what happened actually in Boston to Stony Brook. And the Stony Brook, part of it goes under the Northeastern campus. Stony Brook was very historic river in Boston, but nobody knows it. And people only know Stony Brook train station and Stony Brook Park. But there was a river which was bigger than Muddy River, which is now underground. It should be daylighted. And now the 4th paradigm was after the Clean Water Act. So this is basically, we are now in 4th paradigm here. Developing countries will be still on the 3rd paradigm. Heavy investment in the infrastructure, deep tunnel storage, combined sewer overflows. Basically can be characterized by saying use water collected by fast conveyance, end of pipe treatment, and dumping. So basically this is the 4th paradigm. So we have to go now to changes. So we have problems with the 4th paradigm. Meaning that natural hydrologic status of the urban areas or urban water bodies and watershed has been modified by imperviousness, building sewers and stream modifications, including the burying the streams. This has impact on the remaining streams, which was increased the high flows, more flooding. Peak flows increased by a factor of 4 to 10. It's very difficult to sustain viable population, biota, increased variability of the flow, increased stream bank erosion, etc. There are some problems in groundwater, including problems here in Back Bay area, where buildings were sinking because the groundwater level was dropped because the recharge was diminished. Here is the Mexico City. Actually, this should be horizontal. As you can see, this cathedral is kind of sinking. So, but the same thing with subsidence actually is happening in also Venice, Philadelphia, Mexico City, Boston, and many other cities. We have diminishing groundwater supply. People don't even use any more groundwater, diminishing base flow. So people are realizing that we cannot we cannot meet the goals of the Clean Water Act by the 4th paradigm infrastructure, by 4th paradigm management of the resources and water. So there's not the damages to the streams, again, by wastewater disposal. What happened was when you take water upstream, there is not enough flow left in the streams, like for example in Denver, Chattahoochee River, in Atlanta. And then after this water is used and reused in the city, it's discharges a big, huge effluent into the stream, and that stream then becomes overwhelmed with effluents. We call them effluent-dominated streams. So the other problems are, for example, substrate degradation. The bottom of the rivers are covered by muck and clay instead of gravel and sand. Habitat loss and fragmentation of the habitat, increased peak flows by channel lining. We have channel lining, cutting trees along the water bodies, and decreased base flow. This is one of the worst problems of the urban streams. And the final destiny, changing them into sewers and culverts. We have new threats to water supplies, and we have problems now, maybe not as much in the United States, but it's already coming. For example, 16% of lakes in Florida are so-called hypertrophic. Hypertrophic means beyond eutrophic. That's hypertrophic conditions are characterized by too much nutrients and harmful algal blooms. These are the algal blooms which has millions of organisms, more than millions sometimes, in 1 milliliter. So that's basically a pea soup, as you can see on these slides. The lower slides are actually something I'm a little bit working on right now. It's a danger to the water supply of Prague in Czech Republic. And this is not the reservoir that from which water is taken to Prague. This is a forebay. They have this reservoir is very large. It has got 4 small reservoirs which are already overwhelmed by cyanobacteria algal blooms. We have problems with new chemicals which are appearing in the environment, endocrine disruptors, antibiotics, and pharmaceutical nanoparticles. So people are talking about many things which are now coming to our recognition, and so we have to do something with that. So this kind of was a bleak picture. So now people are starting to think what to do about these problems. We cannot handle it under 4th paradigm. So what can we do? What is the 5th paradigm? What is the 5th paradigm? So here is the vision of this 5th paradigm, which was first formulated by Professor Register from UC Berkeley. 1985, he wrote something about eco-cities. The book was republished again recently. But he defined an eco-city, which means an eco-city which is sustainable, a city which is sustainable, behaves well, everything is balanced, as a city or a part of thereof that balances social, economic, and environmental factors according to this triple bottom line to achieve sustainable development. A sustainable city or eco-city is a city designed with consideration of environmental impact, inhabited by people dedicated to minimization of required inputs of energy, water, and food, and waste inputs of minimization of waste outputs of heat, air pollution, and carbon dioxide, methane, and water pollution. Ideally, a sustainable city powers itself with renewable sources of energy, creates the smallest possible ecological footprint, we will be talking about footprints, and produces the lowest quantity of pollution possible. It also uses land efficiently, composts and used materials, recycles or converts waste to energy. If such practices are adapted, overall contribution of the city to climatic change will be none or minimum below the resiliency threshold. Green infrastructure, resilient and hydrologically and ecologically functioning landscape, and water resources will constitute one system. So we have for this now, so we've been thinking about now, so we have this idea of doing something better, so we have to measure the outcome. And the outcome, we have two very popular measures in United States, which are spreading now all the way to the world. And one is the LEED. Everybody knows about LEED, the Leadership in Energy and Environmental Design, which measures the sustainability of the site, smart location, green design, energy efficiency, indoor environmental quality, innovation and design, neighborhood patterns. And then we have low impact development. Low impact development, this is not a formulation, but low impact development tries to emulate the natural hydrology. In other words, make the city behave like it was a natural hydrologic system. So in this case, these low impact developments, they capture, storage, and infiltrate precipitation, and they mimic the pre-development hydrology. So now the cities of the future, they will necessarily have to incorporate these two concepts into their rules and the way that the cities will be developed. So they should be, they will incorporate LEED and LEED into the consideration, but the cities of the future, as they're coming out, they are not low impact developments. In a way, they have the low impact, but they are not low impact developments which would be characterized by, for example, by low density. This is not the case. So what is the cities of the future? Is it the buildings and neighborhoods conforming to LEED criteria connected to sustainable surface drainage? And we have this problem with this. The problem is that LEED, water reclamation, conservation, and stormwater management criteria, they only represent 15% of the total LEED index. So if we want to have a water-centric, sustainable communities, this may not be the best way to do that. We can say it, water-centric, sustainable eco-city must comply with the LEED criteria, but has to do some other things to go beyond. Some carbon emissions reductions are implicitly assumed, but they're not specifically formulated. Maybe they're now. Now, LEED do not consider carbon emission, but again, implicitly understood they may improve it. They're both basically micro-scale measures. Now, here is another. Now, this is more or less macro-scale measure of the eco-city. This was formulated by World Wildlife Fund, and it's known under One Planet Living. These are 10 criteria, and I've already seen in literature that these are being more and more coming to the forefront and becoming kind of a worldwide yardstick for eco-cities. So zero net carbon emission. It means that there should be no impact on the climatic warming by eco-cities. So means 100% might come from renewable sources. Zero solid waste, well, they say 99%, or only 1% go to the landfill. It implies a lot of reusing. Sustainable transportation with zero carbon emission in the city itself. Local and sustainable materials used throughout the construction. Sustainable food outlets providing organic and fair trade products. 50% reduction in water use from the national average. This is what I'm telling people here and telling you. Extremely easy to do it in the United States because we waste so much water. They're coming to reduce it by 50%. It's nothing, okay? So it's nothing. Just using common sense practices. Natural habitat and wildlife protection and preservation. Preservation of local culture and heritage. Equity and fair trade with wages, so they go beyond, and then the health and happiness. So again, it's nice, but again, we don't have any numbers except that 50% reduction and 100% removal from landfills. So we have to kind of see how to deal with this problem. And the problem of this, why we need to go to these eco-cities and why we need to go the way we try to outline this fifth paradigm. In this paradigm is urban metabolism. And urban metabolism, if you look at the upper picture, you have a city. This city receives materials, food, energy, water, industrial chemicals. Some of them they are not renewable. Most of them are not. And produce these inputs pass through the city, and then this produces outputs, which are on our field would be liquid waste, emissions, and solid waste. So we call this kind of metabolism linear metabolism. I will document that this linear metabolism is not sustainable. So we have to close the cycle. We call it close the cycle. Either be completely cyclic, the complete recycle, or hybrid. Again, we will like to use renewable materials now, not excessive use of resources. Again, materials, food, energy, water, and nutrients, chemicals. Recycle, reuse them inside the city or on site, and then the output will be reduced or no pollution and no waste, or very little waste. I'm again thinking about 30 years from now, when you, young ones, you will be presidents of the companies. So that's what you will be doing, I hope. So we need some macro scale, large scale footprints. A footprint is a quantitative measure showing the appropriation of natural resource by human beings. There are three of those footprints. One is ecological. That's a measure of the use of bioproductive space, for example, hectare of or acres of productive land needed to support life in the cities. The second one is water, how much water is used. We can use liters per capita or gallons per capita per year or per day. And the third one is now carbon. Carbon is a measure of the impact that human activities have, and it's measured in units of carbon emitted to the atmosphere per capita, again, kilograms or tons per year. So if we look at this ecological footprint, so in a nutshell, the Earth today has about 6 billion people, already past 6 billion. In 1995, it's already approaching 7. In 2040, it will have 10 billion people, more or less. We're hoping it will be kind of level off. In 1965, one person required 1.5. There are amount of land available, productive land per one person was about 1.5 hectare, and amount of land available, which will be in 2040, will be less than 1 hectare per capita, or about 2 acres or something like that. Now, if you look at the countries which kind of comply with this 1 hectare per person or less, we will see most cities in undeveloped countries, because the people are really living a bad life. They kind of they have a very hard hardship. They have not enough resources. Countries with 2 to 3 would be Japan or Republic of Korea. 3 to 4, most of the European countries, and countries with 4 to 5 is Australia, Canada, and United States. But what I'm saying, in this 2040, there will be only 1 hectare per person available, and we are using 6. So what it means, there will be a conflict. And these cities in developing countries, they are rapidly developing. Their living standard is increasing. They want to have the same goodies as we have in the United States, but they cannot. They cannot because, if everybody wants to have this living standard in this linear system, it's not possible. It's just the resources are not available. They are not here. So there's a big imbalance. Water use. Okay, again, US is leading the water use, and about 650 liters per capita. Liters per capita, roughly, again, what would be 160 gallons. That's what you hear when you use US units. U.S., Middle East countries, Abu Dhabi, El Paso, Texas, which is in dry region, Dubai, they all have very high water use. If you look, some other cities, for example, typically Europe would have 150 liters. I was just looking at the Prague. Prague is about 110 liters per capita per day. 110 liters. So, can we, in the U.S., reduce that? Can we go from 600 liters to 120 liters? Probably not really soon, but we can easily achieve that 50% reduction. If you look at these eco-cities, and I will be showing some of these eco-cities again, we're talking below the 100 liters per capita. And why the eco-cities, some of these eco-cities, these new cities, why can achieve it? These eco-cities are built in China, in Middle East. They are built in very hostile environments, in brownfields, desert environment that does not have enough water. Tianjin has very little water. So they do have to do that hybrid cyclic water management. On top of the direct use is something which is called virtual use. Virtual use is for producing meat, growing corn, for producing electricity, for making cars. This water has to be used, should be actually added to the water use per capita. Again, this just makes this water situation even more difficult for the future. For example, I put for food, typically farmers and producers and factories which make food or industries which produce the food, then stockyards, they use about 2,000 liters per capita per day on top of the 600 liters. So we have a big problem and we have to somehow deal with it. Here is here are the results of from American Water Works Association study in 1990s of water use in households, by U.S. households. I'm not going to go through every component of that, but you can see that the total indoor is on average, 1990s was 240 liters, maybe 60, 70 gallons per capita, but the total was about 550 or 600 liters or 150 gallons. Most of it total is basically irrigation. People are growing grass, and I don't know why, but they do. So that's why it's what is increasing. The same study now look at the possibility of reducing this water use by available technology. Let's say in that time, for example, people were not using low flush toilets. So now if you use low flush toilets, if you use some of these restrictors on showers, if you do the native landscaping you do not irrigation, you can reduce it relatively easily to 200 liters per capita per day. Still higher than in Europe, still much higher than in Asia, but it would be a great accomplishment. Not only that, if you reduce the water use by this conservation, this has a direct relationship to the energy use. You can proportionally using energy. If you reduce from 600 liters per capita to 200 liters, you probably cut energy use by the same proportion, okay? In water business. Now here are some of these carbon emissions by the cities. I'm again not going to read it, but look at this Qatar on the left side, Qatar, United Arab Emirates. These are in Middle East. They use enormous amount of water, and they pay dearly for it because most of it is desalination. And then they use a lot of energy to get this water. They use a lot of energy for cooling and everything. So the emissions of carbon emissions in tons per year is 56 for Qatar, let's say Canada, 17, Australia, we are somewhere here. And here is what they actually say, were saying in the beginning of this, the third slide. Average US emissions are 19 tons per capita per year. But if you look at the US cities, with the exception of the Washington, D.C., that's a kind of outlier. If you use the US cities, then it is indeed a small portion. It's much less than the average person. So there is something in the cities that makes this GHG emissions smaller, and that's obviously car use of traffic, use of automobiles. Here I would like to show one. San Francisco. San Francisco is on the same level. That's already, you're reaching with this 2 tons per capita, you already reached that sustainable limit. It has the close to what you would expect from a well-behaving city. The same on the same level as, for example, Tokyo. Now, what is so special about San Francisco? Well, you don't drive cars in San Francisco. It's very difficult. You have excellent public transportation. All of it is by BART, which is electric, or electric buses. So it's all electric. They probably have some nuclear power plants now subject to tsunami or whatever, but they have so San Francisco is very high density city. And you will see that these are the parameters which makes these GHG emissions smaller. So San Francisco is on a European level, and again, if they do this 2-3 tons, that's already a limit which you would like to have. And if you can make it by renewable resources, then you're home free. Then you're home, and it can be done. So current urban systems are linear. Excessive water volumes are withdrawn, mostly from distant sources, from Kwabin, for example. And inside the community, water is used only once and wastefully. Treated drinking water is used, for example, for landscape irrigation for growing grass. There's great losses by leaks and evapotranspiration, and water is transferred underground to distant large wastewater treatment plants, and they use excessive amount of energy, emit carbon, often methane, which are greenhouse gases. And then the effluent water bodies are effluent dominated, and so many of them disappear from the surface. Now here is a quote by very famous in the field of ecocity and wastewater technology, Professor Willy Verstraete. And if you just take the name, because he's a leader in this new sustainable waste, we will not call it wastewater anymore, but let's say for time being, wastewater treatment technology. He said that conventional system based on activated sludge wastewater treatment is the wrong way towards sustainability. And we will show why. In this system, linear system, drinking water is primarily used as a transport vector and irrigation. Only a minor part is used for nutritional purpose. Total carbon footprint of an activated sludge wastewater treatment is not sustainable and represents in Belgium or France about 125 kilograms of carbon per capita per year, which could be about 340 kilograms of carbon in the United States. Difference being nuclear power plants and water hydropower power plants in Europe. For example, 80% of electricity in France is produced by nuclear power plants. Here, only about 30%, roughly. Conventional removal of nutrients and potential reuse recycle would require additional energy and would emit more GHGs. Heat and nutrients are generally not recovered. Energy recovered from sludge digestion is rarely practiced and represent only a minor portion of the energy potential. Residual pollution load is still significant. So we have to close the cycle. So here we have some definitions. So I call it 4 R's, 3 S, and 2 T's. And so 4 R's are reduce by water and energy by conservation, reclaim. Reclaim is to treat for safe discharge into environment, basically on TMDLs. Reclaim energy and reclaim nutrients. Reuse after additional treatment. And the 4th R is the restore water bodies because we need them as a resource and as a part of the system. 3 S's are separate, sequester, and store. Separate the wastewater or used water now into blue, white, gray, yellow, and black water. Sequester GHGs and remove and detoxify toxics, and store reclaimed water on the surface and underground. And 2 T's are toilet to tap. Okay, so in some western part of United States, you may have cases where they think that they can reuse the sewage, basically treat it to the point. It's possible. All of this is possible. We can treat sewage today to the level which is commensurate with distilled water or drinking water. It can be done. It has been done. But I'm saying, is it needed? I would say maybe not. So this new concepts, now finally getting to something, this new concept, eco-mimicry of the landscape, develop urban landscape that would mimic but not necessarily reproduce the pre-development natural system. So, minimize imperviousness. Drainage service mostly on the surface. Reduction of energy consumption. Public transportation, non-polluting fuels, electric buses and light rail. Green buildings, passive energy savings, water savings application, etc. You probably know it because this is now a very popular topic of discussion. Green space for recreation, interconnecting riparian buffers and wetlands around the rivers. Urban brownfields remediation and development. I already mentioned that many of these new developments are on brownfields. They're on brownfields or on land which has no use. One of the rules of the eco-city is not to use agricultural land. Ecologically sound stream restoration and daylighting, including base flow improvement. So we have to invent new terminology. This new terminology, for example, wastewater is now used water. Treated wastewater that meets standards for discharge into receiving waters and other non-potable uses is reclaimed water. Reclaimed water treated to potable water quality is called new water. That's a Singapore terminology. Treatment plant without recovery of biogas, energy, nutrient, or treatment plant with recovery of biogas, energy, nutrients is called integrated resource recovery facility. I'm not making them up. I'm partially making them, but it's coming from other. This is already in all over the literature. Blue water, new terminology, is a clean natural water. White water is surface runoff. Black water is water containing urine, feces, and kitchen solids. Gray water is a domestic used water without black water. And yellow water is obviously urine, and because it contains most of the nutrients in 1% of volume. So we can separate. Most surface drainage should be adopt this LEED concept. Most of the surface drainage would be in using ponds, wetlands, rain gardens, stream corridors. We have to restore the first order of streams, of urban streams, because they are not existing, and we have to improve the second order streams. So we can say these urban best management practices, which we were discussing with development of diffuse pollution control, non-point pollution control. Professor Herberger mentioned it. our philosophy at that time was that, okay, the people pollute the land and water, and we develop these best management practices to treat it. We just fix it. That's the philosophy of engineers. You can do whatever you want, but we'll fix it, okay? Now, today's philosophy is don't pollute. So we have to have a system which is not polluting. In this case, we have to incorporate into the landscape things which would also help the landscape to function ecologically and hydrologically. So we have green roofs. We have this Seattle street, which is kind of a lead development. We have these pervious pavements. We use the ponds and wetlands, and there's a plethora of these best management practices we can use. There is not a single one which would do everything, so you have to develop the system that would be working. Now, urban water bodies must be restored in a way, because they will be the necessary component of this new system if they are not. Left side is Lincoln Creek, which I was working in 1980s in Milwaukee. That's one of the first time where urban stream was restored from kind of dead, concrete dead, to something which is functioning. They're still learning how to make it functioning very well, but it's functioning pretty good. In China, in Beijing, they lighted the river, and again they have this beautiful resource now which they can be reused for a number of uses. And in Singapore, this is a Kalong River. Some of you are actually going to Singapore. You know that. So in Singapore, I will be showed how the Singapore works a little bit later. They need this river to provide water. They provide actually the new water, because they don't have enough drinking water. So in this case, this restoration of this river corridor, which is on the lower part, is an integral part of this system in Singapore. So these new rivers, rediscovered streams are integral part of that. What has to be done to make the cities functioning? Here is this interesting case in Korea. This is I use it as what can be done, but I would not recommend to do it in this way. So in 1950s in Seoul, there was a river, Cheonggie River. Cheonggie means river. Actually, the name is something a clean river, but it never was clean river. 1950s, there was quota developments because of a lot of refugees from the north during the war. So there was a terrible river. So people did not like that. Government didn't like it. So they covered it by double-decker freeway. Okay, by double-decker on the right side. Now, in 2002, the new mayor of Seoul was a civil engineer. That just shows that we can be in politics. So he was a civil engineer. He's still president. And he has this vision that to revitalize the center of the Seoul, because this area is near King's Palace, and he was the vision that the way to do it is to bring the river, to bring this Cheonggie River back to life. It's a heavy infrastructure project. The problem which they did, why I don't call it as a good project, is because instead of restoring the flows and base flow and things and treating the water, they pump water from downstream, from the large river. So it is energy demanding. But the way I show it, the reason I'm showing it, because it costs $115 million US dollars, and $150 million US dollars. That's a lot. Lincoln Creek was about $80 million for about 15 miles. This is $115 million for 7 miles over the stream. But the economic benefits to these areas were enormous, both in Milwaukee and especially in Seoul. They claim that the economic benefits of revitalization and making this attractive neighborhood, not attractive part of the city, were in billions of dollars, and a lot of billions. There were several articles in civil engineering about this river. Well, it's a heavy infrastructure. So if we want to restore the system, we have to kind of rehabilitate the system. It will never be the original system. So the components we use, we start, let's say, with the green roofs. We start with the green roofs. These green roofs provide insulation, storage for water. For the water from these green roofs can be captured, and also from the used water can be captured. And we also have to implement water and energy conservation. We have to implement some rain gardens that will take this surface runoff and convey it on the surface. We may have to use pervious pavements. And again, there is a kind of beautifully looking ditch, or let's call it, they still call it rain gardens. Or we can use this, again, system which is now in Seattle, that's Seattle lead development. And if you ask how much flow you get and how much pollution, people say maybe only 10% what it was what it would be if we have a storm sewer or even combined sewer. So the flow load, the system would reduce the flow, and it would reduce obviously the pollution. But these urban streams, these new urban streams which you will be creating, or you will be creating hopefully, they need base flow, because by virtue of the imperviousness there is not enough recharge, therefore they don't have a base flow. So one of the things is actually to build a treatment plant inside the community. And it can be done. This is the Dockside Green development in Victoria, one of the green cities, eco-cities, where they put a treatment plant, and they did the same thing in Singapore and other places. They put a treatment plant inside the community, so the water could be reused in these restored and created surface water bodies. So this is how they have created and we have the same thing. We have similar situation in Foxborough, in Patriot Stadium, which uses this recycle cyclic system. So base flow can be also provided by groundwater inflows, sump pumps in basement, upstreams, cooling water, condensate from air conditionings, etc. This is what's going on right now in Zurich. In Zurich, they decided that they're fed up with combined sewer overflows, and so they capture all the clean water flow. They created these new streams, or restored the streams through the city. They also have a lot of clean water input from upstreams, which used to go into sewers. And again, they eliminating by this combined sewer overflows. And none of the above should enter underground sewers. Now here we have some of these new restored surface drainage. The left upper part is in Berlin, Lanzenbergen Tor. Right one is the Dockside Greens in Victoria. I just mentioned it, and I write extensively about it. Lower left is Hammarby Sjöstad, which is in Stockholm, and Jingjiao in China, which is near it's in Tianjin province. So this is the Tianjin province, kind of things you have to see to believe it. So these are the examples that it can be pretty, it can function. It does not have to be obviously, in some places there was a creek, that's a restored creek. In some places they created the creek. But again, what does it mean? That you don't need storm sewers, you don't have combined sewer overflows, and you can reuse the water on site if you wish to do that. Patrick Lucy, who provided that picture, he wanted to show you that these are solar panels. Okay, that's in this eco-city, and that's actually a city which kind of conforms to this requirement of the eco-city. We have to have, in this case, I already mentioned that we will be using this water inside the city to recreate these streams, reuse it in order to close the cycle. So we cannot have a centralized system. We have to decentralize water management system. That centralized is basically one through system. It might be appropriate if only water conservation considered with no reuse. Okay, what it is, you just implement water conservation and reuse the water coming to the city, and then heat and energy recovery may not be feasible. Water use for toilet flushing and irrigation may not be economical or efficient because you would need dual pumping, piping, and long transfer of the water, of this reused water, of this reclaimed water back to the city. Nutrient biogas recovery and conversion to electricity are less than moderately efficient because you can, for example, produce mill organite like in Milwaukee, where they use mill organite as a nutrient, as a fertilizer. You can use biogas for heating digesters, but not much is available. It's difficult to or impossible to restore urban streams because these streams would not have enough flow. Fully decentralized into small clusters is the most efficient for heat and water reclamation. Energy and labor demanding, but savings on transportation, used water, reclaimed water is used on site. Biogas production, use on and conversion to energy may be efficient in developing countries, but it's kind of touchy here. So we probably may need something which is like a hybrid system, which retains advantages of both systems. So we still need a decentralized system. So we have to divide the system into clusters. We may call them eco-block if they behave nicely. So a cluster or eco-block is a semi-autonomous part of the city that for the most part has its own water, stormwater, and used water management. It may be in size of the large building, high-rise, to a subdivision or section of the city with thousands of inhabitants. A cluster infrastructure distributes water and practices water conservation and reuse, implements energy savings in buildings, provides stormwater conveyance, water reclamation units, because you want to recycle and reuse on site, and you have energy recovery from wastewater. So, yeah, but you should have centralized or distributed biogas, energy, nutrient recovery. And the reason I'm kind of saying it because you don't want to have a methane or hydrogen in the building. That will not work. One match will do it. You should have an ecologically, hydrologically functioning landscape, and they should be interconnected for resiliency. Because if one cluster, if the energy recovery or water recovery unit is not working, then you may have to send it to the next cluster where it is working. This would have an effect on the streams because, as you see on this slide, if the water is withdrawn, there are two slides. One is water, which is a linear system, flow and integrity. If you have a linear system, your water is withdrawn and there's very little water left in the city. I'm talking about not necessarily about Boston because there's Charles River is kind of an exception. And integrity is decreasing because of these low flows and pollution coming from combined sewer overflows or sewer overflows. If you have a distributed system, the CSOs do not happen. And the water flows will be reduced gradually, but in stepwise fashion because you take the water and reclaim it for reuse it for flow, for example, again, and so on. So this integrity will not be distorted or disturbed or destroyed as it would be in the linear system. If you need the water, you can take it from the sewer as to start with. This is Professor Asano has proposed that. You can build these satellite treatment plants around the city what will happen, however, if you reclaim the water and reuse it, then this reused water will not go back into sewer, because it will go into these new streams and to reuse. What will go, however, in the sewer is the sludge and the solids which you produce in this site, in this satellite treatment plant. So that leads to an idea. Why that we may actually concentrate this flow which will be in sewers, sanitary sewers will stay, which will be in sewers will be more concentrated than it is now when you have a lot of rainwater coming into the sewers, because the rainwater will not be going there. So we have a much more concentrated flows carrying a lot of solid sludge and things like that. And that's good. That's good. Now here's an example of the satellite type of the cluster, which is the battery park solar development in New York. They take the used water, they treat it more or less conventional system, but then they reuse it for toilet flushing and sometimes for irrigation. So it is a indication of what the size of a cluster of the cluster. It can be there's thousands and thousands of people living in that complex. So it can be, again, cluster be a size like a large building, or it can be a part of the city. If you need to reuse the water, you have to use these new technologies, which is based on microfiltration, reverse osmosis. You cannot chlorinate, so you have to use ultraviolet rays, and that's energy demanding. So we may have to talk about something which is called water energy nexus, and it means that once you start reducing these flows and reusing them, at some point you stop reducing, but you will be increasing energy demand, because these reverse osmosis units, they use a lot of energy. They use, for example, if it is more or less like a low salinity, they use like 4 or 5 kilowatt hours per cubic meter. But if you desalinate from the ocean, they use up to 25. If you go to Masdar, where the Gulf of Persia is heavily salty, then you use far more than 25 kilowatt hours per cubic meter of water. So we're talking about this energy nexus that once is water conservation in the first phase one. My cursor is not. Maybe I could use it. In this phase one, you're proportionally reducing the energy and obviously emissions. But once you start in phase two, reusing, for example, stormwater and some other kind of rainwater, you have to do some treatment that so this decrease of energy use may be kind of leveling off. And once you go into reverse osmosis and all this energy demanding, you may be actually increasing the energy use. So you might be looking always for this optimum here and see what happens. In the US, 1 kilowatt hour represents 0.6 kilograms of carbon dioxide. In France, about 0.22. I have about 15 minutes. Can you bear with me? Okay. Here I made an example. Again, marginal carbon is the carbon per cubic meter. Total carbon is total carbon from the community. Population 100,000. Originally using 500, but they don't have this 500 liters per capita. So they have to get somewhere into this region where they have only 150 liters per capita available. This is actually El Paso, Texas, okay? Kind of looking, I changed the numbers a little bit, but just for illustration. But they have this 500 liters, but they only have the Rio Grande does not provide much water. They had some groundwater, but they only mine it to the point it's salty. So they have to now go to reverse osmosis, and they have only about 150 liters available of that. So they have to go to dramatic reduction. Now they already noted that if they stop irrigating, if they have some of this green subdivision, they reduce the total energy use, and obviously emissions. But once they started with reverse osmosis, that again, that energy use went up. So it's much worse in Middle East, but again, Middle East, they have a lot of solar energy. Interesting total cycle is in Singapore. Again, a lot of CDMers here, they know this case. Singapore is a very small country, 700 square kilometers, population 5 million. So it's a basically city-state on an island. And they have 4 sources of water. One is, so they call it imported water from Malaysia, but they're afraid they lose it because the Malaysians don't like them and they don't. Then they have fresh water from catchments. This is these catchments here, fresh water. There's not enough of that. Then they have water from the ocean, desalinating water, after treatment they reuse it as drinking water. But that's still not enough, so now they have to go to this closing cycle. So what they have to do is they build a tunnel, and they treat it, use water, then they treat it by very high, part of it goes out the ocean, portion is treated by reverse osmosis, microfiltration, and ultraviolet disinfection. Originally they were using it only for industry, but now they're thinking about putting it back to this freshwater reservoir, and maybe which will increase their water supply by 10-15%. So they did close the cycle, as you can see. But to do that, they had to do complete cleanup of the watershed. So all the sewage must be collected, go to this water reclamation plant. They do the other things, street and household refuse is collected daily. So they're already doing it the right way, but it's a heavy infrastructure. So here is in order to get, so what they did was, and again, there's a CDM project, what they did was they converted the freshwater, seawater estuary. This is the Singapore River, this is the Kallang River portion of the estuary. They built a marina barrage, which changed this estuary into the freshwater body. They had to do all the again BMPs in the watershed to clean up the surface runoff. So this is now much cleaner than it used to be. And they pump now. This is a pumping station here, I believe. They pump the water now to these freshwater reservoirs to supplement what they have. So this is a completely closed cycle. I'm not calling it I'm not giving them clean build of EcoCity yet, but they are very close. The reason why I'm saying they're not yet there because they still have relatively high energy use, but with the vengeance and with the really enthusiasm they have, they will be very quickly on the EcoCity level. Okay. So in order to reclaim, to do it better, we have to switch from aerobic to anaerobic system. We should actually, it's not necessary. So we will have the 3 S's, which will separate, store, and sequester. We will have 3 R's, reclaim, reuse, and recycle. We will have no 2 T's. We will have distributed water and energy reclamation for gray, blue, and white, and some black. We will do we will concentrate the black water with sludge and send it to the regional integrated resources recovery facility. And we will have anaerobic processes which are key. Again, this is building on Verstride and on the people from University of Ghent. Actually, before Verstride was Professor, still very active, Professor Lettinga, he came up with these ideas. So there's a number of interesting projects. So here is I would call it double recycle of the used water produced by, this represents the eco block. This is not just one building. So we have black water loop, we have gray water loop. In the black water loop, we want to get all the solids and all the black stuff out of it. If we can recover biogas, but basically send it to this integrated send the solids and bad stuff to the integrated recovery facility, but keep some water because we will need this water into gray water loop. Now the gray water loop takes water obviously from the baths, from the laundry, and maybe from dishwasher, but it's not showing, and stores it. It has to be pumped. We can recover the heat if you want to. Actually, you should recover the heat. There must be some filtration, sand filtration, because that gray water is not exactly clean water, as you know. This is actually nasty water. There's a lot of pathogens even. Microfiltration, reverse osmosis. If you want to do the complete recycle and reuse it, for example, reuse it for showers and laundry and things like that. You can supplement. The supplement is from water from the grid, and if you put the numbers on that, this is actually, I'm not making up all this, although I did some correction. This is what it's called as a Qingdao double loop. It's a Qingdao eco block which was developed by University of California, Berkeley. Professor Harrison Fraker, some of you may know the name. He proposed it for the Qingdao. He did some things which I would know. For this, in order to keep it going, you need precipitation. And you have to store water during the time of the abundance, and then you have to use it. You can reuse it back for during the time of shortage. Again, this water can be used also for irrigation. So in general, you can do fit for reuse water. You don't have to do double loop. If you, for example, want to irrigate, it would be stupid to take the nutrients out of this reclaimed water. If you for irrigation, because you keep nutrients in. If you want to use it in-house, you have to take them out. And if you want to use it in a base flow or ecological flow, you have to take some nutrients out. Here is kind of a water balance on a dry day, which shows that in order to get a 60 liter, only use 60 liters from the grid, 60 liters from the grid, you have to use all of the other things which we were collecting before. A little bit of excess of the liquid black water. Go to surface storage. You can use it for ecological flow. You can put it back into this double loop for gray water. Would you do it in Boston? Probably not. But again, would you do it in Masdar on this Southwest United States? I would say yes. Okay, so we look at some of these eco-cities. I call it a review of 7 eco-cities. This one is the Hammarby-Sjöstad. This is the Dongtang. This is a virtual city. This is Tianjin, which is being built rapidly. This is the Qingdao. This is Sonoma Valley. They're planning to start again after the real estate market improves. This is Treasure Island in San Francisco. And this is this is actually Masdar. This is Sonoma Valley. Yeah, okay. This is I made a mistake here. This is Masdar. This is Sonoma Valley. You see Masdar here. They should go out. So, if you look at the detail, is Harrison Fraker divided Qingdao into the eco blocks. So this is an eco block, 1,800 people. What he did was something which we would not do. He thought that he can do the black water recycle on site in the wetland. I would never do this way. Okay, you cannot have a black water recycle in wetlands next to the apartment house. But it says he has got wind turbines. He has got solar panels everywhere. He has got recovery he infiltrates all the water on the premises. So this is a complete recycle in Qingdao. Except Qingdao didn't do it, but they did it in Tianjin. But he did an energy balance, and it is self-sustainable of energy. So it's a 100% renewable energy, 100% not 100% recycled, because they do get about 50 liters from the grid. but it recycles a lot. So it is one of those, maybe the future concepts. This is the changing. Now the changing applied these eco blocks here. Eco blocks concept. Professor Fraker told me that they will be using the eco block concept in Tianjin, so we have to believe it. It's a water-centric. They created this stream from which they reuse water. The treatment plant is somewhere in the middle, somewhere nearby, so they can use their water for reuse. They had somewhere a wastewater pond, which is not shown on the picture. So if you look at the results of this, again, I will not go through all these numbers, but look at one thing. So if you look at the density of these eco blocks, let's say the lead in the United States, the density would be 10, 15, 20 people per hectare. Okay? In these cities, the density, with the exception of the Sonoma Valley, is between 100 to 200 people. Then again, Qingdao is kind of an exception. So the density does matter. It is, and also the water recycle, again, Hammarby does not recycle, but they claim they can, with the conservation, they can get to 100 liters per capita per day. Masdar recycles almost everything, but they still have to bring the fresh water by desalination. Qingdao would be recycling a lot. Sonoma Valley, again, 20% would do it because by water conservation, and 20% they will get into this one planet living criteria. The Masdar, Sonoma Valley, and Qingdao would comply with one planet living criteria for eco-cities. Here is a reason why this population density matters. Here is the population density and carbon emission. These are the total carbon emissions from public transportation, heating, cooling, and traffic, and water as well. Water is only a small portion of it. But you can see, if you want to have a completely renewable, 100% renewable, you have to be in this region. You have to be in this region. If you go beyond, it's not necessary. It's not, you may, if land is expensive, but so most of these eco-cities would be in this region, 100 to 200 people per hectare. More, this will be almost the end of it, more centralized resource recovery. So if you now want to get more from, this during this reuse, we have to also do more in energy and in energy reuse or energy reclamation. So in this case, since we have to go to anaerobic, from aerobic, the influent must be more concentrated, around 1,000 milligrams per liter for COD, which would be desirable. There might be a separation of the urine. It's not necessary, by the way. That inflow would contain sludge and other solids, shredded food and other organic solids. Other organic biodegradable solid waste may be tracked in. So you can practice something which is called co-digestion. Because of high COD, the conventional activated sludge would not work. So you have to go to anaerobic anyway. But right now the conventional activated sludge, conventional sludge digesters are not very good. They require very long residence time, and water is still diluted, so it would not work. So what Lettinga and what these people is promoting, and they use this use of upflow anaerobic sludge blanket reactor, because in that thing the residence time is less than 1 day, so much smaller. So we will use these clusters, eco blocks. Let's say here we have these 3 clusters. They do some kind of local reuse or water reclamation, heat reclamation or reuse. And then send the bad stuff, really bad and concentrated stuff, to this integrated resource recovery facility. And the water here would be used mostly for irrigation, water supply, and downstream from the city water supply. That would not do anything to these streams which are in the city. So in this city, if we restore the streams, these streams would not have flow. But again, we can clean this to the level that these streams can be actually used for, this can be actually used for, again, for reuse and for irrigation, reuse, for toilet flushing. And you would have, again, some kind of this double cycle system implemented in the city. There is some energy use, but this should be producing energy. It should produce more energy than it uses. So recycle of energy into the grid. Here are some numbers on how much energy is used in treatment. Activated sludge, roughly, maybe up to 0.5 kilowatt hours per cubic meter. But you can see the desalination up to 20 kilowatt per hour per cubic meter, kilowatt hour, and that would correspond to about 15 kilograms of CO2 emitted from cubic meter of desalinated water. So we have to also recover the nutrients. We are running out of phosphorus. And some people anticipate that by 2040, the net mined phosphorus will be gone. Guano, all these things will not be available. There is no, for example, mining of guano in Europe. There is no phosphorus. They have to import it from North Africa. Now, so we have to recycle phosphorus because without that, agriculture will be suffering. Here is the concept, more traditional, that you have a dry biomass for energy recovery. You have sewage sludge, only sludge. You can do the digestion, or you can do the pyrolysis, where you get charcoal. You get, by additional heating, you can change it to the oil. And here you get, so you can use grass, or you can use the oil. You will have the syngas, which is carbon monoxide and hydrogen. You can use the combustion, or you can produce the electricity. So this is more or less traditional way how to recover heat and energy from the solids. This would provide maybe half of the energy needs for a treatment plant. But we can, there's another concept again by Verstraete. Now you have screening, now you have a concentrator, he calls it concentrator. By concentrating the waste, okay, using ultraviolet filtration, reverse osmosis, you have now solids, concentrated flow. It goes to anaerobic digester, produce the biogas, filter press. You get a nitrogen-rich water. You can go to pyrolysis. You have biochar, and again, biochar has a phosphorus. So this is another concept. He calls it zero waste. Zero waste. He claims that the zero waste, if you balance, can prevent. This is the energy which would be recovered, and energy, and this would be carbon dioxide not released into environment, 88 kilograms per year. In France, it would be about 230 in the United States. So he claims that this would kind of prevent about 4.4% of the global CO2 emissions. Now, in conclusion, I think that looking forward, there are some very interesting developments which we now see in the literature and in the laboratories. Now, obviously, UASB reactor has been here since 1970, so this is nothing new. You can get 0.4 liters of methane per kilogram of COD removed. So that has been around because you collect the biogas here. By hydrogen fuel cells. Hydrogen fuel cell is the one which will convert the biogas into the electricity. And first it converts the biogas into hydrogen, And the electricity will be, again, in this fuel cell, will be produced by letting the protons move through the membranes, separating them in the membrane. So this produces the electricity. Instead of direct contact of the electron exchange, this would be done. By electricity. It would produce the electricity, and it would also produce water because for every 2 CH4 you produce 3 molecules of water. So there's and it also produces heat. So this can go to heating. The CO2 can go to sequestering. Now the microbial fuel cell, it can be done in the reactor. The same thing can be done in a reactor. This comes from from Europe by Verstride, but the Logan in Penn State is doing the same thing. So again, you can get hydrogen. No, you can get electricity, not hydrogen, from this microbial fuel cell. But you can also get hydrogen, and if you add electricity, you can carry this whole process of microbial digestion to in this case it would to hydrogen. So we may have some kind of hydrogen or methane-based or electricity-based integrated resources recovery facility. So here I just plotted it here just for fun. Here is the upflow reactor, upflow anaerobic sludge blanket reactor, produces biogas. You can have a pre-digestion of the solid biomass, but a pre-digestion not to the complete methane production, but to hydrogen production, which can be actually helped by this bioelectrically bioelectrically assisted microbial reactor. If you add a little bit of electricity, it will go. The acetates will go into the hydrogen, not to methane. At this point, you don't have to do that because you want to shorten the detention time. That hydrogen will go to the hydrogen fuel cell. Now, biogas can go to the after steam rendering. It can go to hydrogen too. So again, this produces the CO2. CO2 can be used for. Now let me go this side. The effluent from that will go after in magnesium. We can produce struvite. A struvite is a ammonium magnesium phosphate, which is a very good fertilizer. So you can get the fertilizer out, but that's done with the high pH. So you need CO2 to neutralize the pH, which is the producing alkalinity. After some aerobic trickling filtration, and membrane filtration, you can get water that can be used and reused. You can have, this is also producing heat, so you can have all the heating you need, and there will be excess heat, and you will have electric energy coming out of that. So you can also, this is really wild. You can use that CO2. Here is a kind of algae reactor, concentrating, which will produce algal biomass. I think this is being done on MIT here. So just go on, just do it. Because that CO2 which is produced here, it can help produce algal biomass. This algal biomass, after you separate the water, can go back to these reactors and even produce more energy. So I think this. There are other things. This is the last slide, which we have to EcoCity. This is the transportation. This is the driverless transportation for Masdar. This is with driver transportation in Portland. Looks exactly the same, does exactly the same thing. You have obviously solar panels. You have photovoltaics or heat panels. This is Hammarby-Sjöstad. In Hammarby-Sjöstad, they recycle also solid waste. They sort and recycle solid. They have a very sophisticated system for recycling solid waste. Here is the electric power station for Sonoma Mountain Village, 5,000 people. This will be one of the 3 which will provide enough electricity so it can be, all electricity will be renewable. This is on the individual house. This is how you do it in the green buildings, all the stuff you can do in green buildings. Photovoltaics, passive heating, passive cooling, etc. Here is the dong tank idea for having the wind turbines all over the city. The city of Dongtan was supposed to have 500,000. Kind of it's put on hold and might be developed. A reason why I'm featuring is because these first concepts of eco-cities were implemented in this Dongtan. Most of them were implemented in Dongtan. So one more slide, maybe we can go to conclusion. Water conservation is the best alternative solution to water availability, and there is a relationship between water use and energy reductions. Combined sewers will become obsolete and no CSOs or SSOs, combined sewer overflows or sanitary sewer overflows. Excess capacity of existing sanitary sewers can be leased to cable, which is being done in Tokyo. They're making a lot of money. Reuse with high efficiency solids and pollutant removals in a closed system requires more energy because the energy requirement in the treatment. This energy should and could be provided by renewable sources. Reuse recycle needs makeup water. You cannot do it just complete recycle to offset losses by reject water and liquid content in sludge and possibly by evaporation. A new paradigm of urban drainage and used water use with resource recovery needs to be developed and implemented. These new systems would be carbon neutral and greatly reduce water and GHG emissions. Energy from separated and concentrated used water can be extracted by anaerobic processes in form of methane, and cities of the future as electricity or hydrogen, and by heat pumps as heat. Higher COD concentration and reducing used water volumes of separated black water is a key for efficient anaerobic energy separation. Co-digestion of concentrated used black water, sludge, and other organic solids is possible and should be considered. Nutrients must be recovered. Hybrid system with an integrated resource recovery facility will dramatically reduce water use, could achieve zero pollution, produce energy, heat, fertilizer, solids, and even produce energy, biomass, and sequester carbon. Switch from methane and syngas energy recovery to hydrogen and direct energy is on the horizon. And energy and resource recovery could bring about significant economic benefits when compared to current costs of wastewater disposal and damages to an environment. And here is a little bit plugging of the book, but mainly for acknowledgement. I work with some people, good people. Jack Ahern. Jack Ahern is a vice provost now of University of Massachusetts. He's a landscape architect. Paul Brown, executive vice president of CDM. I got a lot of knowledge and pictures from Herbert Dreisaitl, the best. Herbert Dreisaitl, he's the best land architect of waterscapes. If you are interested in this topic, Herbert Dreisaitl is right here in Harvard now. He's on a scholarship, but he's got offices in Singapore, China, Germany, Switzerland. CH2M Hill, Glenn Diger is the pioneer of that again. Patrick Lucy from Aquatex from Victoria. Public Utility Board, Singapore, and many others. So it's a exciting development. It's a hopefully upcoming development. It may be 20 years, but it's already happening. There's the number of OPL cities are growing. There will be one in Brazil in Turkey, Portugal, maybe in Europe. They're thinking actually one in US, but I'm not going to reveal where because it can collapse any day. So Sonoma County will be a OPL community. Maybe Portland is leaning towards that. Victoria. So it is exciting. It is a new change, hopefully we can call it a new paradigm. Thank you.
If you have time for a few questions?
Depending on how familiar you are with the city of New Orleans, which is a place I have a special interest in, and would seem interesting in the light of the ideas you're talking about, what kind of a fit do you see between these ideas and a place like New Orleans, and where would you see unique problems or realities that might need special attention, adjustments in this kind of approach, or would this approach be just fine for the city of New Orleans?
Well, I'm familiar a lot with New Orleans because in my early years I was working a lot in South, and I had a project in Mobile and New Orleans and on Mississippi River with chemical companies. So I spent a lot of the time on Bourbon Street. Okay, this approach is applicable to any community, even to American suburbs. It's applicable as long as you put your solar panel on the roof and stop using those SUVs and go with electric hybrid cars. And there is not much, again, car traffic in the New Orleans, and you're trying to restore the light rail in New Orleans. It used to be there. It's applicable to any community, but it's more geared towards these new cities, the developing countries, which basically be telling them, don't do American suburbs, just do it, in this ecosystem directions. But New Orleans is now rebuilding, so it could be used there.
I'd like to follow up on that question and ask, what do you think an acceptable level of risk is for these newer cities, where right now in this country, especially for flooding, we've designed to a 1% chance of flood.
Mm-hmm.
What would you say would be an acceptable level of risk for newer cities?
I think it would be the same, because a part of it would be a restoration of these river corridors, and they would be like the one Lincoln Creek in Milwaukee, or Kalanga River there, designed for 100 years for flooding. So risk is the same.
So in the case of New Orleans,
Oh no, that's a different story. Okay.
a lot of our cities are coastal.
Yeah, right. Yeah, coastal cities. They were actually we were talking about in San Francisco about it. So how to do the risk of coastal flooding? I think I don't know what you do against tsunami. I frankly don't know, because the idea is that you do not build cities in the floodplain. That's one of the things you have to recognize. By this new landscape, you recognize what is the floodplain and what kind of development you can have in the floodplain and what kind of development you cannot have in the floodplain. I'm very familiar with Japanese cities. I've been to Kyoto several times. Kyoto the river is relatively small, but I've seen Osaka, which is basically 15 million people living in the floodplain. So they're doing some really monumental things, and I was showing they mentioned it in the discussion, I showed to my class how they do it in Tokyo, where basically Tokyo is two-year flooding. They expect that they get flooded every other year. So they actually build some of the buildings on columns, and the yard is a storage for flood. So they do all kinds of things there just in Japan too. But I think we should stick what we have and delineate floodplains properly with probably the same risk and restore the streams so they could handle this 100-year flood. But it will also include work in the watershed, like they do in Kalang River watershed in Singapore, where they do the watershed restoration as well as the stream restoration. So you have to do both. That's something with the retrofitting. If you build new city, then you just take these rules into account.
So the paradigm that we're in now was driven in the U.S. at least by the Clean Water Act, regulatory drivers. I'm curious where you see how we should be ushered into this next paradigm. Top down, or whether the current cities that are going in this direction now are seeing it more for the benefits, driven locally, that the benefits will pay for the cost of trying out this.
The Clean Water Act doesn't prevent you to do the eco-city. So what's preventing is the kind of inertia of the fourth paradigm. Okay, fourth paradigm is if you, for example, want to do something in here, Massachusetts, you have to have if you do, for example, some of these low impact developments, you have to install the granite curbs. You cannot do it. I think the Charles River Watershed Association tried to implement it here, and they had very difficult problems. Kay Bowditch will attest that they had very difficult problems actually bringing this to compliance with city codes and things like that. That's not in Clean Water Act. The Clean Water Act actually promotes many of these. They promote best management practices. They promote water reuse, the water recycling, everything. But it's more tradition. Tradition has to be shown. It has to be shown by example. These things, not only they work, they bring tremendous benefits. And anytime they restore the stream, these economical benefits are humongous compared to what it was before. I show it, for example, here, that Stony Brook would go through Roxbury, and which is not in these areas which are not exactly, there is nothing there, you know. But if they have the stream going through this area, which is going now underground in the culvert, that would probably bring a lot of the benefits to people living, not only people living there, but a bunch of cafes and overlooking the river and things like that. So it's by example. I believe that as these cities will be sprouting out, there will be good examples.
Yeah, how would the per capita capital and operating costs of an eco-city compare to that of a, let's say, if you were going to build a new traditional city? How do you expect that those capital and operating costs would compare?
I said that many of these things would, the capital cost might be at beginning high, but the benefits that would bring to the economy would be very high. Now, in Europe, when they install solar panels, they actually advertise that this installation of that will pay for the electricity. In other words, in 10 years, the cost of installation of solar energy will be paid off because they save on the electricity. When I was flying in February over Germany, I've seen thousands of wind turbines. And that's just dotted. The whole landscape is dotted with wind turbines. It would not be there if it was not economical. These are mostly privately installed facilities. That's just because they have this. I think it's something which has to do with the cap and trade, and trading of the GHGs. So may call for another economic stimuli or economic thinking. So in Europe, and again, China, the same thing. It's paying off for them. So you can buy a house in Czech Republic for less than 200,000, which would be energy neutral. It will produce excess energy, but they have the system that it can sell it to the power company, and power companies are actually complaining that they're getting too much of it. They will have to decommission some of those terrible brown coal plants, and the homeowner gets paid off. It gets paid off nicely in 5-10 years, so I think it's economical. The developers I met, Patrick Lucy, very famous developer who was making a lot of lectures here, he claims that these operation costs will be free because the electricity they produce and the resources they produce would pay for a lot of operation costs. So I don't know. I'm not exactly, although I teach economics, but I don't play economic specialist on TV, and so I cannot say how the economics would look like. But
Time for one more question. What do you see as the biggest challenges to retrofitting cities in the United States?
biggest challenge? Biggest challenge would be actually persuade people to have solar panels on the roofs and show them it's beneficial. Biggest challenge would be actually to change the drainage. But the drainage, for example, you repave the streets every 10 years. So it will be gradual change where you would maybe switch into side alleys and side streets into pervious pavements, to the reuse, recycle, maybe get people used to that. Instead of drinking water, you flushing toilet with the reused water. So a lot of it is in thinking. But again, if it is a necessity, like in Southwest United States, it's going to happen. It will not be happening here because we have plenty of water. And this tradition of curb and gutter and storm sewers is still very strong.